Hi everyone, it's my pleasure to present this work, MirrorNet, on behalf of the authors from Tencent National University of Singapore and Peking University. And I'm actually not one of the author, I'm just presenting this for them. All right, so let's first talk about why do we need MirrorNet. Before introducing the MirrorNet, let me first briefly describe the production WAN that we aim to emulate. So this is our production WAN in Tencent. It's very large in scale, and it connects hundreds of data centers, supports million applications, and billions of users. And managing such a network reliably is highly challenging because it must handle dynamic traffic demands, plan changes such as upgrades, and unexpected failures such as hardware faults. To support evolving demands and enhance resilience, we adopt a multi-plane architecture. So as shown in this figure, the physical network topology is divided into multiple parallel topologies called planes. So each one of these is a plane. And cross-DC, cross-data center traffic is distributed across these planes using flow-level ECMP. And each plane has a dedicated software-based central controller. They run distributed agents on each router and manages a proportion of the overall traffic. And the multi-plane architecture enables the phase of rollout, upgrades, and maintenance activities, reducing the risk of network-wide disruptions. So WAN involves a controller in each plane to perform centralized traffic engineering, which takes real-time traffic demands into account to continuously adjust the traffic scheduling decisions. So this centralized TE control loop operates periodically and includes three steps. The first is state monitoring, which involves the controller polling agents on each router to discover the network topology and measure bandwidth demands among the sites. Second is based on the topology and demand, the controller runs TE algorithms which allocate paths for every pair of sites to optimize specific goals. And finally, by comparing the path output by the TE algorithm with the existing path, the controller identifies changed path and reconfigures the network using tunneling. So we now present 4 case studies to demonstrate the necessity of MirrorNet based on this. So first, there are untraceable network failures. So as a large-scale backbone network, we typically encounter tens of failures daily from both internal devices to external service providers. And these failures often trigger the TE control system to initiate traffic rescheduling. However, tracking the root causes of these rescheduling events is a significant challenge. For example, this figure shows 4 sites, and each network link is a segment has a uniform bandwidth of 1,000 gigabits per second. So there are multiple terminals, for example, AB, and MBD, and AC. Each assigned with different bandwidth. And an issue across partial link disruption reduced the AB link bandwidth from 1,000 to 500 gigabits per second. So this makes it unable to handle the AB and ABD tunnel total bandwidth. So the TE the TE control system will attempt to redistribute some of the tunnel traffic from the AB link to the alternative route, but because the spare bandwidth on other links was insufficient, so it will lead to a continued packet loss of 100 gigabits per second on the AB link. So we lack detailed running logs due to performance considerations. So this, along with our inability to replace the exact fault and traffic condition, hindered a thorough root cause analysis. So later with MirrorNet, we could recreate this state just to prior to the failure and then introduce the specific fault into our simulation. So this helped us to scrutinize the network's response in a controlled environment. All right, so the second case is that our backbone network involves a lot of parameters, tens of them. And these parameters are critical for optimizing bandwidth allocation. And the process of tuning could just take a lot of time. For example, say if a threshold is too low, can result in frequent or unnecessary TE rescheduling actions, like switching path from just for 1% of the utilization across different links, just as shown here. So this kind of unnecessary traffic rescheduling action fluctuates traffic distribution without actually improving network performance. So this often need new updates to be programmed into switches, which can lead to hundreds of milliseconds of packet losses. The traditional process involves a series of iterative adjustments and testing. For example, after changing parameters in version 0, like scheduling only if link utilization exceeds 10%, version 1 is tested in portion of the network for validation. And subsequent variation will undergo similar cycles, which takes months to reach the final version. So with MirrorNet, we actually have the capability to fine-tune parameters in a more controlled emulation environment. Ensuring they are optimized before deployment, this enables us to more efficiently resolve most of these issues. Right. So, and case 3 is a shallow single-plane testing. So traditional testing methods for multi-plane network architecture often rely on similarities across different planes. And this approach typically involves one plane as a testbed, assuming that successful tests can be replicated across other planes. However, this can fail and may lead to incidents where there are differences between planes. So let's consider a scenario in our network where our objective is to isolate each plane to implement new updates. This process was initially tried on first plane with a plan to replicate it on the other if the first plane is successful. For every plane, the procedure involves sequential revoking routes for each node within the plane. With this procedure worked well for the first, while this procedure worked well for the first 3 planes, it resulted in a substantial packet loss in the 4th plane, as illustrated in the figure, where this is the error. So the underlying issue was that unlike other router nodes using TE to route the traffic, node C in plan 4 lacked this MPLS TE-based traffic forwarding caused by configuration bugs. Okay. So as such, relying on single plane canary testing fails to uncover these deeper plane-specific issues. So we cannot just replicate them. So we need a more thoroughly better environment for us to test the problem. Okay, so finally we have another case where we need accurate capacity assessment. So the lack of precise capacity estimation for failure scenario often leads to critical incidents, and these situations typically arise when traffic flow exceeds the available bandwidth during peak hours, especially when an unexpected disruption occurs. So accurately predicting the network ability to handle such fluctuations is critical, but it poses significant challenges. So essentially, a prior tool cannot really satisfy our demands. Okay. So now let's move on to the design and the implementation of MirrorNet. So based on this case study, we design this MirrorNet. Okay. So this is the overall design. To enhance network reliability, we need to proactively assess the impact of potential changes and conduct in-depth retrospective analysis when unexpected failure happened. So our design of MirrorNet wants to satisfy 3 specific requirements, which are fine-grained, high-fidelity emulation with high scalability and resource efficiency. To achieve this goal, our MirrorNet consists of 2 key components. We have a central controller, emulation orchestrator, and a set of emulation networks. As shown here, step 0, the orchestrator continuously retrieves real-time network data from production network and store it in a database. And then it takes emulation tasks from operator. Based on each task, the orchestrator deploys, The orchestrator deploys 1 or more emulation network as shown in step 1, with their lifecycle managed by the nest manager. Okay. And every emulation network contains a controller and a set of routers, and all of these components are replicated from the production network, so everything is the same. And the translator ensures that each emulation network's state aligns well with the corresponding segment in the production network. Okay, so there are three key techniques which I'll mention later. I'll describe now. To accurately emulate a production network, it requires us to store network topology, including both underlay and overlay information at a fine granularity. So this brings us the first challenge. The network essentially generates massive data volumes. So fine-grained simulation requires strong massive data, which is around 1,300 gigabytes per day for one plane, leading to a huge resource consumption. And as shown in this paper table, we observed that no changes were rare within 1 year, while most changes happen to tunnel information with one change daily per tunnel on average. And all of these changes are not frequent on a daily period. So if we only store the changes instead of the entire data every second, we only need to store around 0.003% of the data volume for IP link information, and also 0.001 for tunnel information. This will significantly reduce the storage resources. So we introduced the incremental storage mechanism to reduce resource. And also previously in the table, observed that node changes can be rare. Based on this fact, the key idea is very simple, right? As we mentioned, we do not store the complete topology at every moment. Instead, we just do this periodically. And to reconstruct the network state at the target time, MirrorNet first loads the closest preceding snapshot from the database, and then replace the sequence of events in order. So in this way, we accurately recover the topology at a specific moment. And to ensure state consistency, MirrorNet compares the reconstructed topology against real-time cached snapshots. So if the reconstructed state matches the cache snapshot, then the cache can be dropped. Otherwise, the cache snapshot is saved as a new reference point. Okay, so far we have discussed how to reconstruct the network state efficiently through incremental storage and replay. However, accurate reconstruction alone is not enough. So in practice, the simulation environment needs to ingest network data from multiple resources, and these data have strong dependencies. So if they're injected in a run order, the emulated behavior can easily deviate from that of the real network. So this brings us to the second challenge, where simulation environment introduces multi-source data, and the incorrect injection order can cause deviation. So to address this, we propose a consistent network update mechanism, where network data should not be injected independently. Instead, they should be injected in a dependency-preserving order. So based on the idea, we organize the update process in 5 steps. So first, we do topology construction, and after that, we do underlay network configuration, and third is overlay network configuration. And then, and the fourth is traffic information injection, and finally is the event information injection. Okay. So to ensure the safe updates of the network, these processes have a strong dependency. Right? This figure shows a dependency tree to guide the network updates. So depending on the specific simulation task, the above task can be sequentially selected. Okay. So furthermore, tunnel mapping is an important part of accurate emulation. So in a production network, multiple tunnels may carry traffic between the same source and destination nodes for load balancing and redundancy. The problem is that in traditional emulation, production tunnels are not always directly mapped to the corresponding tunnel in the emulation environment. So as a result, traffic may be randomly assigned, leading to inaccurate traffic scheduling and unreliable simulation results. To resolve this, MirrorNet established a one-to-one mapping between the production tunnels and also emulation tunnels in advance. So we do this by analyzing the TE database, traffic engineering database, and matching tunnels based on the attributes such as source, destination, link path, and service level. So with this mapping, MirrorNet can inject or replay tunnel traffic and path changes much more accurately. allowing the emulation environment to better reflect the tunnel structure and traffic distribution of the real network. Okay, so far we have discussed how MirrorNet ensures fidelity through incremental replay and dependency-aware safe updates. However, accurate and consistent emulation alone is still not enough. To support the practical WAN troubleshooting and what-if analysis, the system also needs to deploy and run large-scale troubleshooting and what-if analysis. Okay. So this leads to our third challenge, where the traditional platform suffer from extremely slow large-scale deployment due to blocked I/O and resource-intensive bottleneck during concurrent emulation. So this figure shows the difference between the traditional deployed workflow and our design in MirrorNet. I'll skip most of the details, but essentially, we adopt a non-blocked optimization. And also, we have devised our own traffic translator algorithm to avoid to resolve the resource-intensive bottleneck. Okay. So finally, I'll briefly show the gains of MirrorNet. It consists of two major components, as I mentioned, the network and also the orchestrator. So for the emulation network, since the production network contains the order of thousands of nodes and links, we deploy a multi-host GNS3-based emulation environment across multiple physical servers. And each server is equipped with 96 core processor and hundreds of memory, gigabytes of memory. And the orchestrator is deployed in the cloud on a 2-core, 4 gigabytes virtual machine. So it's very small. It provides a set of API to interact with. Okay. So some benefits, as shown in the table, we allow this localizing of TE behavior. So we cannot replicate the exact fault for traditional system. However, MirrorNet can recreate the network's state prior to the failure and correlates to the TE behavior with network events. So we can check if the behavior is expected. And also, another benefit is we can do very careful, very fine-grained parameter training. So I'll probably skip this. And finally, we'll also be able to conduct very accurate capacity assessment. And we're able to capture the evolution of the network. So for example, traditional system, they have this experience-based evolution approaches which suffer from high failure rate in gray box testing. But with MirrorNet, we are able to achieve around 100% successful rate. Okay. So we can safely test the configuration changes and also conduct historical fault injection. Okay. And in general, this is how in addition to efficient data storage, we also achieve extreme speed in provisioning the underlying infrastructure compared to state-of-the-art network work. And you can see that this is at hundreds of times faster than OpenStack and around 8 times faster than GNS3. Right. So some operational lessons very quickly. So we have learned a lot. First, regarding fidelity, virtual devices cannot handle the hundreds of gigabytes of raw data in our raw traffic in our production backbone. So instead of replaying raw packets, we replay traffic demands and metrics from production network. So we can focus entirely on faithful replicating control plane behaviors rather than just replicating the entire data plane behavior. Second, regarding emulation speed, to save time, we accelerate the replay of historical events. However, we learned that speed-up ratio has a hard limit. So the compressed time interval must safely accommodate the TE computation and path reconfiguration delays. Otherwise, consecutive events will collide, crashing the controller's logic. And third, for root cause analysis, diagnosis, testing potential failure points sequentially is too slow for production demands. We use API to do batch deploy multiple twin network and then leverage parallel emulation and traffic sharing to test multiple failure points concurrently, enabling much faster root cause localization. And finally, due to the black box nature of vendor VM, we cannot emulate deep level OS or ASIC hardware bugs directly. However, if any hardware bug triggers a subsequent TE action, MirrorNet will successfully capture that for backward analysis. Okay, and that's all for my presentation on this MirrorNet. Thank you. Okay.